In this session, let us see power angle characteristics. Okay, in power angle characteristics, one thing we discussed about armature reaction. In armature reaction, what was happening? Because of armature currents or armature ampere turns, some flux is coming into the air gap. Okay, so because of that armature flux, net flux distribution in the air gap is going to be changed. Okay, so anyway, some flux variation is happening. Of course, we can discuss in detail, but not required. Okay, so that particular armature reaction can be modeled like a reactance. Okay, just remember this way. Let us see in the detailed course how it is coming and all. Okay, so point here is very simple. Anyway, for armature resistance will be there. For winding resistance, leakage flux will be there. Of course, in leakage flux again there are many types of leakages, back-to-back leakage will be there, slot leakage will be there, and many types of leakages will be there. So forget about that, somehow leakage will be there. Okay, and armature reaction flux or armature reaction also let us include in the reactance only for time being. Okay, in detail course I will deal in detail. So my internally induced voltage is EF. Okay, why it is happening? Because of field current. For example, this is field current. Because of field current, internally induced voltage is there, and in the armature resistance will be there, and in the armature leakage reactance will be there, and because of armature reaction one more reactance come. So if I model this as RA, if I model this as XAL, and if I model this as XAR, okay, so this X is coming into picture because of armature reaction, this is coming into picture because of normal leakage, so net is going to be XS. Okay, and synchronous reactance, and this current is IA at an angle pi, this is going to be terminal voltage VT. Okay, so let us draw one small phasor diagram for this. Okay, simple, one resistance is there, one reactance is there, that's it. So let me take VT at an angle 0, terminal voltage at an angle 0. So for example, if it is VT at an angle 0. Okay, now about IA and angle pi in an isolated generator. If the generator is isolated, depending upon the load connected, my power factor will be there. If the load connected is lagging in nature, IA should lag. And if the load connected is capacitive dominated, my IA will lead. So for example, let me consider at lagging power factor loads. Okay, means that my IA should lag behind. Okay, now this angle is going to be pi. Okay, now VT plus IARA plus IAXS is going to be here. Now VT plus IARA in the sense IARA is the voltage drop and current flowing through resistance is IA, both should be in line. Current and voltage will be in line in what do you say, resistance. So IARA. Okay, now if you think of reactance, okay, so IAXS. Okay, IAXS is the voltage and IA is the current flowing through inductor. Okay, so in an inductor current should lag behind voltage by 90 degrees, so voltage should lead current by 90 degrees. If IA is here, IAXS will be 90 degrees lead, it will be here. So IARA plus IAXS is going to be EF. Okay, so this angle VT to IA, this angle is called as delta. Okay, so that delta is going to be torque angle or power angle. Why torque angle and power angle is same in synchronous machine only? Because in synchronous machine it will rotate at constant speed. What is power? Torque multiplied by speed. If speed is constant, okay, so under that condition, depending upon the torque only, power also will be there. So torque angle and power angle will be same only in synchronous machine. Okay, now coming to the point, this is going to be XS is going to be very high. Why? For example, if you compare this synchronous machine with induction machine, in induction machine armature reaction will not be there. Okay, so only XAL will be there. And for example, let us start from transformer. In transformer, X by R ratio should vary between 2 to 6, we discussed. Okay, and in induction machine, leakage will be more because of some reasons, we will see in detail course. So X by R ratio of induction machine is higher than than transformer, and for that there is no difference between induction machine and synchronous machine from XAL point of view. On top of XAL, XAR is added, so XS by R ratio of synchronous machine is going to be highest. Okay, so XS by R ratio is highest. For example, if I think of resistance is 1 ohm and reactance is 10 ohm, such that X by R ratio is 10. Okay, so what is the magnitude? Magnitude of this is going to be under root of 101. 1 square plus 10 square under root is going to be roughly 10 only. 10.00 something will come. And if you think of angle, means tan inverse of 10. Okay, almost it's going to be more than 85 degrees or 87 degrees. So resistance we are going to neglect. Okay, so normally even in practical conditions of synchronous machine also, armature resistance will be neglected because X by R ratio is going to be high. Okay, so if you consider resistance, okay, so in DC machine we use same copper, in induction machine we use same copper, annealed copper, and in transformer also we use same copper, in synchronous machine also we use same copper. So armature resistance will be same in per unit among all the machines. Okay, but in DC machine this will not be there. Okay, so the moment a leakage is not there, only armature resistance will be there, so that armature resistance has to be considered. Okay, now next is going to be X by R ratio will come into picture for transformer. X by R ratio will vary from 2 to 6. An induction machine X by R ratio at least should be more than 5. And in synchronous machine X by R ratio should be more than 10. Means that the moment X by R ratio is going to be very high, armature resistance can be neglected except in calculations of efficiency and heating. Okay, so from cooling point of view, like temperature rise, in order to find temperature rise, armature resistance will be considered in practical conditions, and in finding efficiency we will consider, except these two, normally in practical conditions also armature resistance will be neglected. Okay, anyway, point here is, what is IA here? IA, so IA is going to be, with respect to VT, EF should be at an angle delta plus delta. Okay, with respect to VT, EF should lead. Now EF, this voltage minus this voltage by ZS. So this is going to be EF at an angle delta minus VT at an angle 0 divided by this particular ZS at an angle theta S. Let me call it as RA plus JXS. Okay, so this is going to be ZS at an angle theta S. Now in an alternator, which is more important, not inside power, but how much power is coming out of these particular terminals. Okay, so let me consider that as S output. S output. So how much is S output? Is going to be VT IA complex conjugate, P plus JQ format, if it is lagging. Okay, so VT IA complex conjugate, in the sense VT into IA complex conjugate EF by ZS at an angle theta S minus delta. Okay, delta minus theta S will come, and in complex conjugate theta S minus delta will come, minus VT by ZS at an angle theta S. So what is the equation here? EF VT by ZS at an angle theta S minus delta minus VT square by ZS at an angle theta S. Okay, so this is going to be VT square by ZS at an angle theta S. Now what is output power? Basically, as of now we are doing generic equation, okay, by considering RA, but after some time we will neglect RA and we will run the show. So because very recently one question came, they included armature resistance or kind of transmission line resistance. In that, many guys felt much difficulty, but anyway we are not going to remember anything, only can't we do this step and this step? Yes, over. Now let us think of power output is going to be how much? EF VT by ZS cos theta S minus delta minus VT square by ZS cos theta S. Okay, now when output power is going to be maximum, for example P out, because they can ask at P output maximum, what is the condition? Okay, now can I say theta S? Okay, for example if cos theta S can be minus 1, under that condition this plus minus of minus will become plus, it will be increased. No, why? Theta S is not the variable. Okay, theta s is the machine constant that will be decided by, theta s will be decided by xs by Ra, which is constant. So we should not think like a mathematician. You please think like a electrical engineer. For example, as we discussed previously, if it is the pole, if it is reference, n pole, s pole. Okay, for example, if my prime mover is keeping it ahead, okay, so back torque will be there. Back torque will be there. So for example, if I keep at 45 degrees, back torque. If I keep it at 50 degrees, back torque will be more here. Okay, so means depending upon the torque in the sense I'm going to apply, prime mover is going to apply some torque, back torque will be there. For example, both are like this. Okay, this is going to be reference and this is going to be my rotor pole, n pole, s pole. If both are rotating like this, what is the torque developed? 0. For example, if it is placed here, back torque will be there and prime mover will not allow it to go back. Okay, so torque will be 0 here, torque will be increased. What is the angle between these two? Delta. Okay, so which is variable here? If input torque from mechanical side, if input torque is the variable, delta is going to be variable. So we should not say cos theta and s can be minus 1.5 because theta s is constant. What is variable here? Variable is delta. Okay, so when you are going to get P output maximum, when this quantity equal to 1, means that cos theta s minus delta should be 1 or theta s minus delta should be 0, or I can say delta equal to theta s. Okay, mostly question will not come. Even if question come, we are going to do this. Okay, for example, let us think of Q output. How much is Q output? Same sign will come. So F Vt by Zs sin theta s minus delta plus minus Vt square by Zs sin theta s. Okay, again what is the variable? Delta is the variable. Okay, now when Q output is going to be maximum, when this is going to be 1. Okay, so at Q output maximum, the condition is going to be this should be 1, or I can say theta s minus delta should be 90 degrees. Or delta should be equal to theta s minus 90. Okay, so in this condition Q output will be maximum. But anyway, if you come to the gate, okay, in gate also most probably with RA question may not come. Even if it come, like we have one volt gate question, I will tell you how to solve. Means when RA is neglected. For example, let armature resistance is neglected. Why? Because XS by R is going to be high. If you consider XS, it will be fine. Under that condition, for example, if I think of P, okay, so RA is 0. RA is 0 minus, means that theta S is going to be 90. Okay, so cos 90 minus delta is going to be sin delta. And cos 90 is going to be 0. So P output is going to be EF Vt by XS sin delta. Okay, is it output or input? I did not tell you anything about losses. Okay, now let us think of Q output is going to be this when theta s is going to be 90. So 90 minus delta cos delta, so it is going to be 90. Okay, so under that condition this is going to be F Vt by XS, because Zs will become, Ra is not there, XS, so it's going to be cos delta minus Vt square by XS. So in this Vt by XS into EF cos delta minus Vt. Okay, so Q output, you have to remember this equation. Of course, we will solve multiple problems such that you will remember. Most of the times, like EF Vt by XS sin delta, everybody know. And here, like whether it is like as of now, don't bother whether it is overexcited, underexcited. I will take care of all those. Okay, so Q output, you have to remember Vt by XS into EF cos delta minus Vt is going to be the Q output. About this in detail, we will see in the next video. For example, if I think of P with respect to delta. So what is this? EF Vt by XS sin delta. So with respect to delta, it's going to be sin delta. Okay, what is maximum power? P max is going to be F Vt by xs when delta is going to be 90 degrees. Okay, here I have to tell you why after 90 torque development will be less, because the power or torque is same, because power multiplied by synchronous speed omega s, which is constant, is going to be torque. So this can be torque also, torque or power. Okay, why after 90 degrees? Because it is very important for stability and all. Okay, why after delta equal to 90, this is going to be 90 degrees. Why after delta equal to 90, torque development is going to be less? For example, let me think of, this is a reference, this is S pole of the resultant, this is going to be N pole of the resultant. Okay, now let us think of my poles. Okay, if my poles are here, my field poles are here, this is going to be N pole and S pole. It is rotating with omega s, it is also rotating with omega s. Then how much is the torque developed? 0. Okay, now for example, if I push this ahead, actually in machines we are going to discuss about steady state conditions only. Okay, now this is going to be N of the field pole, this is S. Now torque will be in opposite direction, because Ns attraction will be there, this is the torque. But how it has to rotate? It has to rotate in this direction, this is going to be omega s. Okay, so who is who is stopping this particular pole not to go back? Prime mover. So prime mover will give torque in this direction, supply in this direction, torque will be in backward direction. So my torque developed is against to the direction of rotation, it's a generator. Now for example, if I think of here, N pole here, S pole here, under that condition again torque will be in opposite direction. Okay, if I go with more than 90, for example 0, delta equal to 0, delta less than 90, delta equal to 90. Okay, if it is more than 90, for example, let me think of more than 90. Now you will understand. Okay, then also, okay, if I compare these three, what will happen? For example, let us take reference of red. Okay, in red what is happening? NN repulsion will be there, NS attraction will be there. And here yes, NS attraction will be there, yes repulsion will be there. Okay, such that you are going to get, from theoretical point of view, analysis point of view, forget about equations. So when delta is maximum, 90 degrees, you are going to get maximum torque. For example, if it is here, okay, Ns attraction will be strong, but Nn repulsion will be weak. That's why back torque will be less. If I keep it here, Nn repulsion in backward direction, for example, in this case also torque will be in this direction only. Okay, so especially this discussion is going to help you much in salient rotor machine, which will come soon. Okay, so if you compare here torque and here torque, okay, here is going to maximum torque. Now here if you see, attraction is more, repulsion is less. Here if you see, repulsion is more, attraction is less. So maximum is going to happen when delta equal to 90. When delta equal to 90. Now if you come back here, okay, for example, blue condition, when delta is less than 90, power or torque will be there. When delta is more than 90, also same torque will be there. Okay, but here at delta equal to 90, maximum torque is coming. At delta less than 90, torque will be reduced. At delta more than 90, torque will be reduced. Okay, now if you see, for example, this is the reference S pole. Okay, this is the reference S pole, this is the N pole. Okay, now for example, if both are rotating like this, torque development will be 0. For example, if I keep it here, my prime mover is keeping it here, both are rotating in this direction, what is the torque? Torque will be in opposite direction. Okay, now if I keep it here, delta is going to be 90 degrees, torque is going to be maximum. Okay, so who is actually, now you will understand why steady state stability limit is 90 degrees. Okay, so here point here is, if I keep it, who is keeping from here to here? Prime mover input. When prime mover input is more, it will go here. If prime mover input still more, it will go here. If prime mover input is maximum, it will go here. From here, if I increase prime mover input, okay, so input is increased, input torque is increased, but back torque is reduced. So it will, rotor will accelerate. Okay, so point here is very simple. Okay, if I keep it here, okay, my prime mover input is more, then when my prime mover torque equal to back torque, it will be stable. Prime mover torque is increased, prime mover torque is increased to maximum. Okay, so beyond delta equal to 90, if I increase more power input from the prime mover, but back torque is going to be less because back torque is going to be maximum here. So back torque is going to be reduced, but prime mover torque is going to be increased. So that will give you accelerating torque such that my rotor will continue to accelerate. Okay, now means with these characteristics we can directly connect to stability. We can directly connect to any part of the power system which is linked with synchronous machine. We will see soon.